So today, I know I'm presenting this a little bit different, but I was kind of hoping if we weren't in hybrid learning, we could all discuss in class. So I'm kind of hoping maybe this will still give us a little bit of the discussion format as we sort of walk through or talk about things here. So today we're going to be talking about causation versus correlation. And this is a really critical piece of understanding data. These terms are often misunderstood or maybe misrepresented. And we often see data being presented in a way that wants people to think that it's a causation when it's really not. So knowing the importance between these and really being able to think about these terms critically when we're looking at data is going to be a key piece of what we're doing this week. So when we are talking about causation versus correlation, the first thing is just to understand what those words mean. So causation is saying that we have a direct cause and effect. Without a doubt, we have enough data to prove, not just sort of suggest or show. We can prove without a doubt that when one thing happens, it is causing another thing to happen. This often needs extensive research, data collection, or studies to be done to actually show that we have a causation happening. So a causation is never something that we just sort of repeatedly observe or something that we notice seems to be a trend. It has to be something done much more extensively. So for example, we have medical research that shows taking something like Tylenol or ibuprofen is leading to relieve a headache, right? So taking ibuprofen relieves a headache. We can say that that is true because we have extensive research that shows without a doubt that medication can cause you to not have a headache. Okay, but this doesn't happen very often. It's something that's rare, even though people think it happens frequently. It doesn't happen that often. More likely, we have something like a correlation. Okay, the word correlation is just saying that for some reason, two things are related to each other. So over here on the left, you'll see this table is showing temperature. Notice the temperatures in Celsius. I know we usually use Fahrenheit, but in the science world, that doesn't happen very often. So the temperature based on ice cream sales. Okay, and if we sort of then take that data and we plot it over here, we sort of notice how, right, it looks like we have this upward trend that as it gets warmer outside, we're more likely to sell more ice cream, right? So we might make the statement that we sell more ice cream the warmer it is. That's not a causation. Now, it does seem that there's some relationship there, that two things are related, that the temperature might have an effect on how much ice cream is being sold, but it's not a direct cause and effect. There could be other factors in play. Maybe it was always warmer when it was the weekend and more people were likely to buy ice cream on the weekend. Recognizing that something is a correlation really requires you to do some more abstract thinking, some more critical thinking to really sort of question what else could be going on. Correlation is more likely what we are going to be talking about. Now, it doesn't mean that two things don't affect one another. It just means that we don't have enough data to prove that it's a direct cause and effect and that other factors could be at play. We have different types of correlation. As we go throughout this week, we'll sort of look at that. So we have correlation that is positive, okay, because it goes uphill. So just like we would think positive slope and negative slope, positive correlation is going to be increasing. So as one goes up, the other goes up. Negative correlation is going to be decreasing. Okay, so we have it going downhill. As one goes up, the other goes down. Okay, and the more closely linked they are, the more likely they'll look like a line. Okay, so the closer they are to a line, the stronger relationship that we have. And then we also have the idea of what could happen is that we have no correlation at all, and that we have data that's randomly spread, and it seems to show that there's no link at all. So we wouldn't even be able to make a statement about it. There would be no link, there would be no relationship. The key to this is to not forget to think. Okay, so we can have numbers say something, but we still need to use our brains at the same time. So data might seem to show a correlation, But that doesn't necessarily mean they're actually linked in any way. We can find data that looks like it's showing something. So it's really important that we're using our brain at the same time. And again, just remember, correlation means that there is no cause and effect. There can be a relationship, but we can't show cause and effect. Okay? It could also mean that for some random reason, the two things tend to have what looks like a relationship, but if we use our brain, it doesn't at all. And I'm going to show you what I mean by that here by looking at some of these sort of ridiculous examples. I actually already have it pulled up, but there's a link there. So in this website, there's tons of ridiculous examples. It's basically making the statement that just because on a graph, it looks like we see a correlation between two things, it doesn't prove that they're actually linked together. It definitely doesn't prove a causation. And so we need to use our brains at the same time. So for example, here's a graph of cheese consumption being compared with people who died by becoming tangled in their bed sheets. Now, I wasn't even sure that that was really something that could happen, but someone has collected data on this, right? And if we look at it, right, it looks very similar. As one goes up, the other goes up. As one goes down, the other goes down, right? They sort of follow this very similar pattern. Okay, but if we use our brains, hopefully we would realize that cheese consumption probably has nothing to do with someone dying by becoming tangled in their bed sheets. Okay, so just because we can get data that looks like two things are related, it doesn't necessarily mean that they are. And you can scroll through here. There's tons of them. So here's one with divorce rate in Michigan versus the amount of margarine that someone consumes, someone eats. Again, they look very similar. Looks like there might be a relationship, but we know with our brains that that's not actually happening. Okay, so just all sorts of ridiculous things in here, right? Total revenue generated by arcades versus computer science doctorates awarded in the US, right? So just because we look at data and we see it looks like they have a relationship, we have to make sure we're using our brain at the same time because it doesn't always guarantee something. Now, there is something you've sort of seen, and I've sort of been ignoring it on these slides of talking about a correlation coefficient. Right back here, we saw this number down here, and I just ignored it. But there is a way we can calculate a correlation coefficient. Okay, it comes from this really complex formula we see over here. I'm not going to ask you to ever do that by hand by any means. Okay, we use technology to help us calculate that. And we're going to take a look at actually calculating that a little bit later this week. Okay, but it is represented with the letter R. And the correlation coefficient is always in between -1 and +1. So just like we said on that previous slide that we can have negative correlation or positive correlation, the closer that correlation coefficient is to -1, the more it's going to look like a line going downhill. Okay, the closer it is to +1, it's closer to a positive correlation. Okay, now looking over here, if we sort of then look at that number, right, 0.9, this is really close to 1, and those points make a pretty straight line. Whereas over here, right, we're only getting 0.6, and while, okay, we might sort of generally see they're following this uphill trend, it's not really that close to a line. Okay, so you'll never have to calculate that correlation coefficient by hand. Okay, just know that we can get one, and that number is going to relate to whether it's a positive correlation, a negative correlation, or the closer it is to 0, no correlation at all. So here are some examples. My students tend to think, oh, perfect, I get these. It really does require some more thinking than we might normally think about it. So for example, researchers found a positive relationship between the happiness of elderly people and the number of pets they have. Okay, so in a study they conducted, so they found out that there was a positive relationship, positive correlation between the happiness of elderly people and the number of pets they have. So more pets, you're happier. Okay, so we can then make the statement, having more pets causes elderly people to be happier. So based on what you've heard so far, do you think that this is a causation or a correlation? This is a correlation. So, I mean, right, research is supporting the fact that more pets cause someone to be happier, but we don't actually know that that's a direct relationship. And we don't know that that's a direct cause and effect. Maybe people who are happier have more money and therefore they can afford more pets. Maybe people are more willing to have pets if they're retired. And so if you're retired, you're happier. There's all different types of factors that could be at play. So this is just a correlation. So we have a graph here that shows how many crimes are in an area, okay, as well as the number of coffee shops that there are. So from looking at this graph, we can say having more coffee shops will lead to more crime. Do you think that this is a causation or a correlation? This is also just a correlation, right? Again, we have data, we have this uphill line, we have even the data points looking pretty straight, right? But probably more likely is what's going on is there's more coffee shops in larger cities. And in larger cities, there's more likely to be more crime, right? So probably not necessarily the fact that more coffee shops are causing more crime, right? Not a direct cause and effect, but some relationship that in bigger cities, you might have more coffee shops and you might have more crime. Okay, so here we have a statement that says ice melts when exposed to heat. Oh, that's the typo there, but the higher the heat ice is exposed to, the faster the ice will melt. So is that statement a causation or a correlation? The higher the heat ice is exposed to, so the more heat ice is exposed to, the faster the ice will melt. Do we think that that is a causation or a correlation? This one is a causation, right? We know without a doubt, heat melts ice. The hotter it is, the quicker it melts. That is just science, right? We have enough research to back that up. We know without a doubt heat melts ice. So this is a causation. Okay, so I know that's sort of just a starting point. We're going to talk about this more in class, but hopefully this helps give us a good idea of what causation is versus correlation.